Now the density matrix rho hat pure for a pure state in any arbitrary basis will contain matrix elements which are non-zero. So I can write down rho hat pure is equal to sum over k comma k prime phi k psi I phi k prime phi of k prime, and this quantity we will identify as a of k star I, and this quantity we will identify as a of ki. So this I can recast as k comma k prime phi of k rho k k prime, which is consistent with our definition that we had earlier, except that now I have changed the labels, and rho k k prime take the form aki ak prime star of I. So you see that now you have matrix elements of the density matrix which are non-zero, although you started off from a pure state. For a pure state, you should also note that rho square pure, it's a projection operator, therefore you know that psi I is equal to psi I, which is rho hat pure. So for any pure state, if you want to determine whether a given density matrix, if you want to determine whether a given density matrix corresponds to a pure state or not, to a pure state, you have to check the condition rho hat square pure must be equal to rho hat pure. It's a property of the projection operator for this. Now for any general density matrix where I have rho hat as sum over I rho I psi I, so this I can write down as sum over k prime phi k psi I, and then I have psi I phi k prime phi of k prime. So there is a rho I sitting outside over here, so this one I rewrite as phi of k rho k prime phi of k prime, with rho of k prime is sum over I rho I, this one is aki and this one is ak star I, so you have aki ak star I. If you now take this quantity, so rho kk, the trace, the sum over the diagonal elements, then you will see that this is going to be sum over rho I, sum over k, aki, ak star I, which is sum over rho I, sum over k mod ak square, rho I sitting over here, which is sum over I rho I, and this is equal to unity, right? Because this is equal to 1 follows from the normalization of the wave function, and sum of total of probabilities over I rho I must be equal to 1. So this is the normalization condition that we can have. correct? Good. So further, note that this is a Hermitian operator, right? So I have rho of k prime as sum over I rho I a k I k prime star. Let's see. This is a k prime, this is k prime. Please, I do make such silly mistakes, but you have to be careful with these things, right? So rho of k prime star then becomes sum over I rho of I a k star I a k prime of I. Then this quantity rho k prime k, essentially the transpose you are looking at, is rho I a k prime star I a of ki, which is exactly rho k prime. So this essentially tells you that this is a Hermitian operator, and therefore since it's a Hermitian operator, its eigenvalues are real numbers. So now we want to discuss the time evolution of the density operator del, and we will start off with this expression, right? And for this we will write down the density matrix as sum over I rho I in the most simplest of its form, psi I, right? So this quantity then becomes, sorry, this has to be rho I, and then this becomes del t. So there is an IH bar multiplying outside, del t of psi I E rho I psi I of E. So in the earlier expression we had this as the subscript of the energy eigenstate, so that is okay. So in fact we understand that the system evolves, so this is the wave function, many particle wave function, and it evolves according to the Hamiltonian, right? So sum over I plus, there will be three terms, II dt psi of I plus psi I rho II del psi I del t, right? So IH bar del psi I del t is equal to H bar of psi. So this is in fact eigenstate of the Hamiltonian, and if such is the case, then we also know that minus H del t psi I is equal to psi I times H bar, and this quantity is 0, right? So if we use this, then we can very easily see that the answer is going to be, the first term over here is going to be H hat psi I rho II psi I, right, minus psi I rho II psi I H hat. So sum over I. Since the Hamiltonian, the sum is over just this, I can write down this as rho hat minus rho hat times H, so which is the commutation relation H hat rho hat. So I H bar d rho dt is this quantity, and this equation is called the von Neumann equation, and this is the counterpart of the classical Liouville equation that we had derived. Now with this, if I set d rho dt is equal to 0, this means that H hat rho hat, the commutation of this is equal to 0. So the Hamiltonian and the density matrix commutes with each other. So therefore this equilibrium probability densities, if I want to look at the let's just equilibrium probability density. So if I want to construct that, then I can very well use the energy eigenfunctions, in which case this rho hat is going to be diagonal in that representation, right? So now, we'll come back to this, but we want to take a look at the density matrix from a different perspective, right? So suppose I have a system, right? Now this system I can split in two parts. In one of the parts, the coordinates are psi, coordinate psi, and in the second one the coordinate is x, right? So the total wave function of the system is psi x comma t, and I know that the evolution of this wave function is governed by the Hamiltonian of psi x comma psi, right? So now let's say I have an observable. S which only depends on x, and the eigenfunctions which form a complete set are given by phi n of s, right? In which case I can write down x comma t is equal to Cn of psi comma t phi n of s with a sum over n. Good. So if I am given any arbitrary observable, if I am given any arbitrary observable f, and I want to calculate the expectation value of f, then you see that I can write down this as sum over, this is going to be n comma n prime phi n prime, and I'm going to have Cn of psi comma t times Cn prime of psi comma t. So this phi n of s, it depends only on the coordinate x. That is something which you must remember, right? Now strikingly, if you look at this expression, then this expression is rho of n prime m. I can identify this quantity as phi n s of x f phi n. So you see that in this average psi of f psi, this average of this observable f, essentially I have the same statistical expression that I had, which started off that this is my quantum mechanical average and this is the probability with which I find the wave function, and therefore you see that the effect of this density matrix is nothing but the effect of this system with coordinate psi on the system on which this observable is defined, right? And this system is what is called the bath, right? So this is an alternative interpretation of density matrix. So now we want to look at form of the density matrix. And for this, I am looking at the equilibrium distribution. Therefore, I know that the Hamiltonian and the density matrix commutes with each other, and this essentially means that if I work in the eigenfunction h of phi n in the energy basis, then I know that the density matrix is going to be diagonal, right? Now, for a microcanonical ensemble, I know that this density is 1 over omega for energy which lies between E and for the energy which lies between E and E plus delta E. This is for the classical case also. We have seen that, right? Otherwise, here for the quantum mechanical case, I am going to have delta. Sorry, this is going to be delta H minus E with a sum over omega, where omega, since I am working in the energy eigenfunction basis, if the energies are discrete, I have En minus E, right? So now, since I'm working in the energy eigenbasis, the density matrix will be diagonal. Now, in a microcanonical ensemble, in the classical statistical mechanics, we had seen that the rho classical for E was 1 over omega, where omega represented the number of microstates within energy E and E plus delta E, and is equal to 0 otherwise. So for a quantum mechanical system, we can write down this one as 1 over omega, the density matrix, rho hat, as delta H hat minus E. And since trace of rho hat is equal to 1, this would imply that omega of E is given by delta of E minus En. Right? For a canonical ensemble, I have rho hat as e to the power minus beta H hat 1 over set. So that again we use the condition trace of rho hat E is equal to 1, and this would mean that I have Z is equal to trace of e to the power minus beta H, which is sum over n, because I'm working in the energy representation, minus beta En. So that Z is clearly going to be a function of beta, right? So this is for the canonical partition function. Sorry, we'll write down that canonical ensemble, and this is the canonical partition function in the energy representation. The average of any quantity, any physical observable, is trace rho hat f hat, right? Which is going to be trace of e to the power minus beta H hat f hat divided by trace of e to the power minus beta H. And if I want to calculate the average of this Hamiltonian, if I substitute f hat as identical to H hat, which is equal to the average energy, it's going to be trace of e to the power minus beta H hat divided by trace of e to the power minus beta H, and which you immediately see, and this is del beta of trace of ln. So we will write it down as, so this is 1 over trace of e to the power minus beta del del beta of e to the power minus beta h trace of this, right? So this becomes minus del del beta of ln z tvn. So which is the result which we obtained for the classical statistical mechanics in the canonical ensemble, right? The average of the entropy is minus kb average of ln rho hat, which is minus kb trace of rho hat ln rho hat, right? And now if I want to use rho hat as e to the power minus beta h divided by trace of e to the power minus beta h, I can substitute this quantity over here. This becomes minus kb trace of e to the power minus beta h hat divided by trace of e to the power minus beta h hat times log of e to the power minus beta h hat divided by trace of e to the power minus beta h hat, right? Good. So this is minus kb trace e to the power minus beta h hat trace e to the power minus beta h hat. Actually we want to keep this, we do not want to write it down explicitly, we will write down rho hat, and let's expand the log. Then this becomes minus of beta h hat minus ln of trace e to the power minus beta h hat. Note that this is just a number, so therefore you have minus of kb, and just look at the first term. This is minus beta trace of rho hat h hat, and you have minus ln trace of e to the power minus beta h hat times, what do you have? You have trace of rho hat, but trace of rho hat is 1. So essentially you have kb beta kb trace of average of rho hat h hat is the average energy E, right? And this one is ln trace of e to the power minus beta h hat. But this quantity is the canonical partition function, so we will write down this as average of S is equal to this. So you clearly see that T of average of S is average of E minus ln of Z, right? So that average E minus there has to be a kbt here because you are multiplying throughout by kbt. So there is a kb here because kb multiplies throughout, and this is nothing but average of t minus kb ln of z, which is average of s, and therefore one has t of average of s as e minus kbt ln z, so that kbt, wait a minute, this has to be a plus sign over here because minus kb is being multiplied, is being taken inside. So minus kb is being taken inside over here, and therefore this becomes a plus. So I have plus plus. So a minus of average KB, minus of KBT ln Z is average of E minus T of S, and which we identify is the free energy. So nice correspondence with classical statistical mechanics. So then we look at the grand canonical ensemble, and here the number of particles are not fixed, so we replace n by the operator n hat, but this operator is different. So now that we have looked at the canonical ensemble, we looked at the grand canonical ensemble, right? Now here, of course, the particle number is not fixed and n is replaced by the operator n cap. So for a fixed system, we have this operator n cap, and the corresponding density is given by e to the power minus beta En mu n divided by capital Q, where since trace of rho is equal to 1, this implies that Q is sum over n comma n e to the power minus beta En e to the power beta mu n, which is again e to the power beta mu n z to the power n sum over n, where this is the canonical partition function and Z is the single particle partition function, and for a non-interacting system, right? The same way we have done in classical statistical mechanics. Of course, we identified small z is equal to small q there. There is nothing special about the symbol. You can as well use small q. Now, so the average of the entropy is trace of rho, sorry, is kb ln of rho hat, right? So the same way that we had used it, minus kb ln rho hat, which is minus kb trace of rho hat ln rho hat, right? So minus kb trace, we'll keep the rho hat and we'll write down ln rho hat as minus beta En minus mu n over q, right? I'm sorry, if this is the Hamiltonian, then this has to be, this is the density operator, so one has to be careful over here. Anyway, we can use that interchangeably, because otherwise this will mean the matrix. If you write En, it means that the matrix element in the energy basis, right? So we have h hat n hat, right? So then this is minus kb trace rho hat minus beta h hat mu n hat minus ln of q. So that the first term is kb trace of, we will write down this as minus rho hat h hat, and then we will write down plus mu trace of rho hat n hat minus, this quantity is just a number, so this becomes ln q. If I now put everything together, there is a beta here. I'm sorry, there has to be a beta here and there is a mu beta here. So this becomes average energy by T plus, this is minus, if I now multiply throughout by minus, this becomes mu by T average of N minus plus Kb. So this minus and this minus makes it plus Kb ln Q. So I have average E minus T of average S minus mu of average N is going to be minus kBT ln Q. And this quantity in the left hand side is the Grant potential. So we have the Grant potential as we got it in classical statistical mechanics.